Cut-through switching is a way for a switch to get minimal information about where a frame is destined and start forwarding that frame as quickly as possible. And I've given you a simplified version of a layer 2 frame on screen. This is a layer 2 frame. It's simplified because I didn't bother to show a few bits that are kind of leading up the frame called the preamble, and I grouped together the layer 3 and the layer 4 headers and the data. But in general, this is the basic structure of a layer 2 frame. And as soon as this frame begins to go in the switch is going to look at this MAC address. Remember how big the MAC address is? It's 6 bytes in size, 48 bits. This 6-byte MAC address is examined, and the switch says, well, based on what I've previously learned, I know that that MAC address lives off of a particular port. So as soon as the switch receives just this much of the frame, it can start forwarding that out of an appropriate destination port. And the benefit of this is we decrease latency inside of the switch. The switch does not have to see the entire frame before it starts to forward the frame. So advocates of cut-through switching would say it's faster than something like store and forward switching. However, because we start sending the frame almost immediately, we don't know yet, or the switch doesn't know yet, if it's a valid frame. Maybe it's messed up. We haven't even come close to interrogating the frame check sequence here at the end to see if there is potentially an error in the frame. We just say it's going to this MAC address, I trust that it's a good frame, and off we go. But to bring you up to date just a little bit on cut-through switching is starting to become fairly popular again in some of Cisco's data center switches. Cisco has a series of data center switches called Nexus switches. And in some of those Nexus switches, cut-through switching is actually used. But it's a more advanced flavor of cut-through switching. The switch can look beyond just the destination MAC address. The switch can also look at the ether type. And the ether type might say this is, for example, an IP version 4 frame. An IP version 4 frame, maybe there's an access control list that's blocking this frame. Maybe it shouldn't even be allowed to go through the switch. Maybe it has a quality of service marking up at layer 3. Maybe we should interrogate that to see if we should treat this differently. So with this more modern approach to cut-through switching that we might find in a Cisco Nexus 5000 series switch, for example, yes, we look at the destination MAC address. We can also check the ether type, and if it's something like an IP version 4 frame, that can tell us to go look into header information in layer 3 headers to check out things like quality of service information, or to see if we might be blocking this frame with some sort of access control that's configured on the switch. But basic cut-through switching, what you're responsible for understanding for the CCNA exam is that with cut-through switching, as soon as the switch sees those first 6 bytes, as soon as it sees the destination MAC address, it can start forwarding that frame, therefore decreasing latency. The downside is we might forward a frame that's a corrupted frame, and we haven't taken the time to check that out yet. With store and forward switching, a switch wants to make sure that a frame is valid, that it's not corrupt, before it starts to forward it out. After all, that would just waste bandwidth if we're forwarding corrupted frames. So what the switch does, it waits until it receives the entire frame. Not just the first 48 bits, not just the first 6 bytes, the destination MAC address, in other words. It waits until it receives the entire frame, and it looks at this frame check sequence. And the switch is going to calculate, using an algorithm, it's going to calculate its own frame check sequence. So the switch creates an FCS of its own. And if the FCS in the frame equals the FCS calculated by the switch can conclude with reasonable certainty that this is a valid frame. It has not been corrupted in transmission, therefore I feel comfortable forwarding it out toward the destination. Advocates of store and forward switching would point this out, saying that we're not going to waste bandwidth by beginning to forward a frame that's invalid anyway. because we're going to be checking the frame check sequence calculation embedded in the frame with our own calculation, and if they match, it must be a good frame. The downside is that this might be a little bit slower than cut-through switching because we are waiting until we receive the entire frame before we begin forwarding that frame. We could almost consider fragment-free switching as a compromise between cut-through switching and store and forward switching. One of the big benefits of cut-through switching was that the switch didn't have to see the entire frame before it started to forward it out towards its destination. However, it didn't check to see if it was valid or not. Maybe a collision had occurred. Maybe the frame check sequence didn't match up. With store and forward switching, we would get the entire frame stored in the switch, make sure it was good, and then start forwarding it. I suppose it's good that we made sure it was a valid frame, but we were introducing some delay by having to receive the entire frame before we started to forward the frame. Fragment-free switching is somewhat of a compromise. Fragment-free switching states that most collisions that are going to occur within a frame are going to occur within the first 64 bytes. What fragment-free switching does, it looks beyond just the destination MAC address and beyond the source MAC and beyond the ether type. It will actually look 64 bytes into our frame, and because most collisions occur in the first 64 bytes, if it doesn't see that a collision has occurred in the first 64 bytes, it has some assurance that this is probably an okay frame. We didn't go to the trouble to wait for the frame check sequence to arrive and do a calculation, so we're not being as thorough in our checking as we would with store and forward switching, but at least we have more assurance that the frame is valid as opposed to cut-through switching. To sum up, fragment-free switching is going to examine the first 64 bytes of a frame. If it does not see that a collision has occurred, it is then going to forward that frame based on the destination MAC address. Let's examine how frames flow through a switched network and how MAC addresses are learned by those switches. On screen we have 3 different switches, and I included a hub as well. And this reminds us that a hub does not have a CAM table. It doesn't have a content addressable memory table like a switch does. A hub doesn't learn anything. We call it a bit spitter. It takes bits in on one port and it just regenerates them out of other ports. So it's not really making intelligent forwarding decisions. It's a layer 1 device. The switches, they are layer 2 devices. Let's say that we have a frame, it's an ARP packet specifically that's going to be sent out in the network, but at layer 2, at the frame level, the source MAC address is the MAC address of PCA. PCA, it's wanting to communicate with PCC as an example. And it knows the IP address of PCC, but it doesn't know the MAC address. How does it learn that? It can send out an ARP broadcast. An ARP broadcast, that's an address resolution protocol broadcast that gets flooded throughout a broadcast domain, and we're asking the question, can somebody tell me the MAC address that corresponds to this IP address? That way we can form a frame that has an appropriate destination MAC address. Right now, PCA doesn't know the MAC address of PCC. So in this ARP packet, we have a source MAC address of all A's, and these would not be MAC addresses that you would find in the real world. I just used all A's, all B's, and all C's just so that we could easily look at a MAC address and identify it so that we could associate it with one of these PCs. Now the destination MAC address, this is the MAC address that you would see in the real world. It's all F's. And all F's MAC address is a broadcast MAC address. And there will never be a device on your network, like a PC with a network interface card, that has an all F's MAC address, so it will never be learned by a switch. And what does a switch do when it receives a frame and it doesn't know the destination MAC address of that frame? It hasn't learned that MAC address is living off of a particular port. The switch floods it. And by flooding a frame, we mean that we're going to send a copy of that frame out of all of our switch ports other than the port that the frame was received on. So in the real world, you really would have a destination MAC address of all F's. Let's see how this frame flows through the network. The frame goes into switch 1, and even though we're destined for the all Fs MAC address, switch 1 notices the source MAC address. It's all A's. And it learned that that source MAC of all A's, it came in on switch port 1. And it makes a note of that in its CAM table. This is another way of saying the MAC address table. CAM, again, stands for Content Addressable Memory. We could use those terms interchangeably, though, CAM table or MAC address table. Now that the switch receives this frame, it learns something. If anybody ever wants to get to PCA, we now know where its MAC address resides. We don't have to flood a frame going to PCA. But in this case, we're still trying to get to the all Fs MAC address, and we don't know it, and we will never know it. We're going to flood it out, all of the ports other than the port that the frame was received on. So switch 1, it floods that frame out of port 2, and it goes into switch 2, port 1. And switch 2 says on port 1, I just saw this frame come in, and it had a source MAC address of all A's. And this is an important point. PCA is not directly attached to switch 2, but still it's available off of switch 2's port 1. That means that switch 2 wants to add to its CAM table that all A's MAC address is available off of port 1. Sure, it's a switch hop away, but that's okay. It's still available off of port 1. Switch 2 is going to now flood this frame. It goes out of ports 2 and 3. When it gets to switch 3, it came in on port 1. Switch 3 makes a note of that. Switch 3 says, I just learned off of port 1 that there is a device with a MAC address of all A's. It adds that to its CAM table. Now the hub, it doesn't learn anything. It's just a repeater. And it's going to just repeat those bits and send them down to PCB, which will say, this isn't for me, and it will discard it. Switch 3, it's going to flood that frame out of port 2. It's going to go to PCC, and it's going to say, that's not for me, and it's going to discard it. But that completes this initial ARP broadcast from PCA out to our network. And over time, the other computers on the network will start to speak as well. Let's say that PCB sends an ARP packet at some point. We've got a source MAC address of all B's, and we're going to a destination MAC address of all F's, the broadcast MAC address. The packet goes through the hub into port 2 of switch 2. Switch 2 is then going to make a note in its CAM table that off of port 2, I've got a MAC address of all B's. It then floods that frame out of ports 1 and 3. This is going to cause switches 1 and 3 to learn how to reach the all B's MAC address, and they're going to flood that frame out of their ports, and those PCs, PCA, PCC, they're going to say, this frame isn't for me, and it's going to discard it. But in the process of doing this ARP, notice what happened. All of the switches now know how to get back to the MAC address of all B's. And for completion's sake, let's say that PCC sends out an ARP packet. The source MAC address is all C's, the destination MAC address is all F's. We go into switch 3. Switch 3 learns that the all C's MAC address lives off of port 2. Switch 3 floods that out of port 1. It goes into switch 2, port 3, and switch 2 makes a note of that available off of port 3, we've got the all C's MAC address. It's going to flood that frame out of ports 1 and 2. The hub is not going to do anything other than just regenerate those bits and send them down to PCB, but switch 1, it made an update to its CAM table to say that the all C's MAC address, the way we get there is we go out of port 2 on switch 1. The frames go down, they hit the PCs discard them, and at this point, we have fully populated the CAM table for all 3 of our switches. Of course, in the real world, we would probably have lots of additional devices, not just 1 or 2 PCs hanging off of a switch. We would have lots of PCs potentially. And we could have larger CAM tables, but this illustrates the logic of how a CAM table is built. Now that we have a populated CAM table, let's send out a frame that's not a broadcast this time. Let's say that PCA is sending a frame to PCC. In other words, the source MAC address on this packet is the all A's MAC address, the destination MAC address is the all C's MAC address, and we're going to see this time the frame doesn't get flooded. PCA sends out this frame into the network, into switch 1. Switch 1 interrogates its CAM table, and it determines that the all C's MAC address is available off of port 2. And even though we only have one other port on switch 1 in this example, we could have 10 other ports, and switch 1 would not flood that frame out of all of those ports, because it knows that to get to the all C's MAC address, we just go out of port 2. That's what it does. it sends the frame out of port 2. It goes into switch 2. Switch 2 looks at the destination MAC address it's all sees according to its CAM table. That's available only off of port 3. No need to send it out of port 2. We send it out of port 3 into switch 3. Switch 3 says, the all sees MAC address I learned, that lives off of port 2, and it forwards it to the destination PC. That is an overview of how a switched network is going to learn where different devices live. The switches learn based on source MAC addresses. Then, when a frame comes into one of those switches, trying to get to a destination MAC address, and that MAC address has been learned earlier because it was earlier a source MAC address, the switch can intelligently forward that frame out of an appropriate port instead of having to flood it.